Now let's just go way back to the quadratic, and what we know is that if the two solutions or the two roots of this equation are alpha and beta, then it should be possible to factorize this quadratic into two linear factors, x minus alpha, x minus beta, but multiplied by a because it's not necessarily monic. Now if I expand the right hand side out and then group some terms, then we can get a direct relationship from what we said yesterday. When we have polynomials that are identical, then we equate the coefficients. So therefore, alpha plus beta must be minus b on a, sum of the roots, and alpha beta must be c on a, product of the roots. That's where those two little formulas come from. If I wanted to create a quadratic equation then that has solutions 2 and negative 3, then I can simply go, well, okay, I know the sum of them is negative 1. I know the product is negative 6. Therefore, that equation must have been x squared minus the sum of the roots, x, and then plus the product of the roots, and there's our equation. Now the advantage of that is if we don't have nice integer answers, it simplifies this immensely, because I don't have to expand the whole thing out. I can go, well look, the sum of the roots here will just be 4, and the product of the roots is negative 1. Therefore the equation it came from was x squared minus 4x minus 1 equals 0. A heck of a lot quicker. Well, if alpha and beta are the solutions to this particular equation, the standard sort of things I ask, okay, well what is the sum of the roots, what is the product of the roots? So minus b on a, 3 on 2, product of the roots minus a half, but then sometimes they like us to play. So what's alpha squared plus beta squared? Well, that's basically using our expansion rewritten, and we go, well, that's got to be the same as alpha plus beta all squared minus 2 alpha beta. And we've found those two things. I can substitute in what we've found, bit of manipulation, we get our answer 13 on 4. Now I've boxed that because that result comes up a heck of a lot. So knowing that the sum of the roots individually squared is the sum of the roots squared minus twice the product of the roots. Reciprocal is also a very common one they like to look at. Well, you know, what alpha plus beta is, well, what's the reciprocal of them added together? And it's not as simple as just turning each one upside down, because we've got an algebraic fraction, and we end up with sum of the roots on the top of the fraction, product of the roots on the bottom of the fraction, and that tidies up nicely to be negative 3. What about this sort of question? Find the value of m. So we don't know what the constant is here, but what we do know is one of the roots will be double the other. Well, instead of the roots being alpha and beta, I'll say, well, one's alpha, the other's twice that, 2 alpha. Sum of the roots becomes negative 6, and the product of the roots is m. And that's what we're trying to find, of course. But over on the left-hand side, we can actually work out what alpha is then. So alpha is negative 2, substitute it into the right-hand side, and we eventually, there it is, we get our answer of m equals 8. So that's just the quadratic. But we can push that idea through to any dimension at all, so any order that we like. So quadratics, we just saw, sum of the roots is minus b on a, product of the roots is c on a. When it comes to a cubic, we push that idea through to the next dimension, or order of polynomial, and it's still true. The sum of the roots is still minus b on a. Thing is, we don't now call the next one the product of the roots. It's all the possible pairings. So I have alpha beta plus alpha gamma plus beta gamma. So we tend to call that the sum of the roots taken 2 at a time. But that would still be c on a, but now we have this new one where it's possible to get all 3 roots and multiply them together, and that will be minus d on a. And we can keep pushing that idea through to move up to a quartic. Once again, the sum of the roots will be minus b on a. Sum of the roots taken 2 at a time, and there will now be 6 different possibilities we could have there, that will still be c on a. But all the possible ones where we take 3 at a time will be minus d on a, and now we can create a new one where we get all 4 of them, that would become e on a. And we could keep going and keep going. So to generalize it, if I've got a polynomial like this, then the sum of the roots 1 at a time. So a nice shorthand way of writing that rather than having to write alpha plus beta plus gamma plus delta plus epsilon plus however many you've got. We just say, well, sigma, because that's our notation for sum, is minus b on a, and that's sum of the roots 1 at a time. Sum of the roots 2 at a time will always be c on a. Sum of the roots 3 at a time will be minus d on a. Sum of the roots 4 at a time would be e on a. And if we were to keep going, sum of the roots 5 at a time would then become minus f on a, then sum of the roots 6 at a time would become g on a, and so on. So it keeps alternating, minus plus, minus plus, minus plus, all the way down. But again, that idea pushes through as well. So if I want to find the sum of the individual roots squared, that will always be the sum of the roots 1 at a time squared minus twice the sum of the roots 2 at a time. It's true for any degree of a polynomial. Let's now play with a cubic. We're going to find, for some insane reason, we want to know what this value is. I don't know what purpose it serves, but there you go. We want 4 alpha plus beta plus gamma minus 7 alpha beta gamma. Well, the first thing I'm going to do is I'm going to find those key things, because there's going to be more questions to come. And we got 1 at a time would be 5 on 2, 2 at a time would be minus 3 on 2, and 3 at a time is minus a half. The one I've got is 4 lots of 1 at a time minus 7 lots of 3 at a time. Substitute in 27 on 2. Ooh, what about the reciprocals of each one? Okay, algebraic fraction. Bottom becomes product of the roots. The top becomes sum of the roots 2 at a time. Substitute those in, and we get, hang on, that should be positive 3, not negative 3, isn't it? Sum of the roots squared, which we now know, okay, well that's going to be the sum of the roots 1 at a time squared minus twice the sum of the roots 2 at a time. Sub into that one, 37 on 4. So still all the same ideas and the techniques we saw for a quadratic, we're just pushing that idea through to the other dimensions. Here's a very old question. So alpha, beta and gamma are roots of this cubic. I guess the first one was just a little gift mark. Oh, find alpha plus beta plus gamma. Okay, well, 0. What would have caught them out is, I can imagine a lot of people would have wrote down the answer 3. But of course there's no x squared term, so it's 0, not 3. So be careful with things like that. You know, don't go too quickly. Make sure you're reading the question. The product of the roots, okay, that one would be negative 1. And then they ask the standard ones, so, well, okay, what's the reciprocal? And so we do our algebraic fraction. We haven't worked out 2 at a time yet. That's the one that will be negative 3, so negative 3 over negative 1. Positive 3 this time, 2003. This time we know 2 of the roots of this particular one are reciprocals of each other. We don't know what they are, but we know they are reciprocals. Work out what k is. This time I'm going to say the roots are, well, alpha. One of the other roots is the reciprocal, so let's call it 1 on alpha, and then I've got a third root that I don't know. Well, I'll call that one beta. So there's my 3 roots. What information can I gather? Well, I'm going to go with the product of the roots straight away, because if I'm dealing with a number and it's reciprocal, when I multiply, that's just going to be 1. So I don't actually need to know what alpha is, but it then allows me to find that other root straight away. So I've got beta is negative 3. Therefore I know, using the factor theorem, that polynomial negative 3 must equal 0. I can now just substitute that in and work out k. K is 13. I can imagine, I mean, it would work. I mean, you could have done, let's do sum of the roots 1 at a time, and you come up with alpha plus 1 on alpha plus beta, then do 2 at a time, create all these simultaneous equations. I mean, it would work. But just because this is roots and coefficients question doesn't mean we can't use other knowledge that we know to save ourselves time. Cubic polynomial. This time there's r, s and t we don't know, they're just real numbers. We have real zeros, 1 alpha and negative alpha. Find the value of r. Well, in this case, when I've got alpha and negative alpha, I know when I add them together it'll disappear. So it does make sense to look at 1 at a time. It also makes sense to look at 1 at a time because r is the coefficient of x squared. So we get simply that r is negative 1. Find the value of s plus t. So I'm not asking us to find s and t themselves. Just what are they when they're added together? Well, 2 at a time, because I've got to get s in there somehow, and that's going to be 2 at a time. Playing around with that, I get that s is minus alpha squared. But of course I don't know what alpha is. And let's have a look at 3 at a time, because we've got to get t in there. So 1 times alpha times minus alpha is negative t. Hang on a sec, look at that. T is alpha squared. Remember, they don't want us to find what t is and what s is, but merely what s plus t is. Well now, s plus t is 0, because alpha squared and minus s alpha squared will cancel out. Another way I could have done that. I could have said polynomial 1 is equal to 0. Remember, they told me 1 is a 0. And if you substitute that in, 1 plus r plus s plus t is 0, we worked out r was negative 1. S plus t is 0. So again, using factor theorem, I can make myself a quicker question here. So 10f, playing with the roots of a polynomial.